Good afternoon, everyone. I am Ganga Hettiarachchi from Kansas State University, and I added my two graduate students actually work on struvite. Struvite is not the only recovered nutrient products that we are working on, but I'm going to present today. My presentation will be basically looking at struvite for this talk. And so I don't think I need this slide for this audience. But just to tell you that the struvite you all know is the ones that reclaimed from wastewater. That's what we know. But if we look at now, if you go to St. Louis or Austra's new research facility, you will see that not just reclaimed struvite, because reclaimed struvite itself cannot really get a market for that because the production is not meeting even 10% of the phosphorus need. So because of that, they are actually doing manufacturing struvite as well. So here in this talk, I'm presenting mainly looking at how this reclaims struvite and manufactures struvite behave in soils, different types of soils. So when we look at reclaimed struvite, this is from the reclaimed from using Ostera technology. Not almost like 95 to 99% that is struvite. And if you do XRD, you will see that you have very less the other materials, but the crystalline materials is mostly struvite. But manufactured struvite, they manufacture using, it doesn't make sense. They manufacture using monoammonium phosphate and then adding magnesium salt to it. And then that one, you could see that the struvite content, it's a mixed product. It's not just struvite. Although it called as manufactured struvite, it has other type of phosphorus, ammonium phosphates, and other phosphates in it. So that's a major difference between this reclaimed and manufactured struvite. And then, like I said, that is because that they could not really get a market share just by producing reclaimed struvite. So we looked at different ways, like how struvite behave in soil, and then also trying to understand, since we were doing it in a plantless system, that how roots could be impacting, root exudates could be impacting struvite solubility by adding different organic acid mixtures. And I don't think I have time to focus on that. So I'm going to focus on the first part where we were trying to understand the fundamental behavior of struvite and what type of reaction products they are making and under what kind of circumstances we can use struvite as a fertilizer. So the objectives, so to assess the solubility, mobility, and reaction products of these both reclaimed and manufactured struvite in 3 contrasting soils, and then also determine how it is impacting the potential plant available P. So our hypothesis was when we are comparing these two soluble fertilizers or the conventional fertilizers, the reclaimed or manufactured struvite will release phosphorus slowly. And then it depends on soils as well. So we use for the studies that I'm going to present today, share today, we use mildly calcareous soil from Garden City. So it is nowhere calcareous like you could find in South Australia or some other places where you could have like a 70% or even more calcium carbonate. These are just mildly calcareous soils, and then acid soils from Brazil, and then a neutral soil from Kansas. So we use the one that I'm sharing, we use control, and then the manufactured struvite, reclaimed struvite, and then monoammonium phosphate and use equal amounts of phosphorus for each of these treatments. So the way that to understand the diffusion behavior, what kind of reactions that they go through, what kind of reaction product that we can see in soil. So we have this design approach where we use petri dishes and then pack soils. Those are packed with like just a slightly moist soils, and then we add the remaining moisture to bring it to about 60% of maximum water holding capacity of that soil. So it's about close to field capacity, not exactly field capacity. And then incubate it for overnight, or if you are concerning about adding moisture and increasing microbial activity, enhance microbial activity by that, and impact of that on the nutrient chemistry, you could actually incubate it longer. So we usually incubate it for overnight and then introduce the fertilizer product, either granule or liquid, to the center, and then cover the center slightly, and then cover the petri dishes, and then incubate those in a controlled environment, usually 25 degrees Celsius. And in these experiments, so we had different sets, actually, although I say we, Amila did this experiment. He's sitting over there, so all credit should go to him. So the one set is sacrificing at 2 days, 1 week, 2 weeks, 5 weeks. So likewise. And then the set of experiments, some sets we went up to all the way up to 12. So at the end of the experiment, so the petri dishes will open, and then we start sectioning those from center to outward. And so here in this one, we used smaller size petri dishes, and then the center section was only 4 millimeter. And then the 7.5 meter diameter, the radius for the second section, and then the third section up to 15.5, and then the 27 millimeter. So that allows, analyzing those sections separately will allow us to understand how far phosphorus diffuse, how fast those phosphorus diffuse, and then we can also have additional petri dishes, since when we section it, we are getting very small amount, so very limited tests can be done. So we have some, the complementary or the replicated petri dishes where we either extract granules, if we do have granules still remaining, and then look at it, look at the speciation of it, or like take the soil and do the X-ray absorption near structure spectroscopy to understand the speciation. So this can be applicable to not only to phosphorus, this can be applicable to any nutrient that we want to study. So this protocol that I'm presenting can be studied, can be used for any nutrient, and then may need to do different modification based on the nutrient and based on the transformation you could expect. For example, nitrogen, you would expect gaseous and things like that. So it would be, the setup would be a little different than phosphorus. Phosphorus, luckily, you don't have that kind of transformation. So it's easier. And the same kind of setup you can use for copper, zinc, the micronutrients, if you're interested in studying micronutrients. So I'm presenting only two soils, the one that the mildly calcareous soil, and then the acid soil one. So the mildly calcareous one had about 7.8% calcium, free calcium carbonate, and then the pH was 8.7 in 1 to 10 soil water. And then the Brazil soil, which is acid, so that one had 5.2 pH. And then you could see the amorphous iron, the extractable, the aluminum, etc., that could impact the phosphorus reaction products in acid soil. So so I'm going to first show the phosphorus diffusion. So to do that, we calculate percentage of phosphorus added. So we can calculate using, I'm not going to go through the equation, but we can calculate what's the percent of P added in the each section. So subtracting the control. So the 2 weeks and 5 weeks, I chose to present those two so that you can see the difference. So monoammonium phosphate, the diffusion is not as great as in other soils, in calcareous soil. Actually, in this soil, diffusion is greater than normally what we would see in calcareous soils. You would see that regardless what phosphorus fertilizer you use, those are going to be mostly going to be retained in the first section. But again, remember that here the first section is the just up to 4 millimeter. Okay, so the radius is very small. So because we wanted to study the struvite and what's happening to phosphorus in there. So what you can see that 2 weeks and 5 weeks, most of the phosphorus from both manufactured and reclaimed struvite stayed within that radius of 4 millimeter diameter section. So it didn't move compared to monoammonium phosphate. And then the other study, there was another study that Nishadi, another graduate student of mine, did, and she compared series of conventional fertilizers, the same story. The other fertilizers, some, especially ammonium polyphosphate, usually has a little bit greater diffusion, but the other ones also, compared to other soils, diffusion is not that great in calcareous soils. So we actually prepare thin sections out of these petri dishes to do microexperiment mapping to understand how phosphorus is diffusing, like visually see phosphorus diffusion after 5 weeks. And we also can, so this was done at Brookhaven National Lab, National Synchrotron Light Source 2. So there we can actually map calcium as well, just to see what's going on. Since it's a calcareous soil, we looked at calcium map as well. So you can see the top ones showing calcium and phosphorus map of 5 weeks incubated reclaimed struvite, and then the bottom ones are showing calcium map on a left-hand side and the right-hand side phosphorus map. So manufactured struvite, what we think as like it dissolved, but really it precipitated out again as calcium P. So you can see that when you are looking at matching of the calcium map and phosphorus map, it is obvious that they are coinciding. So suggesting that although it dissolved, it precipitated out, so it's not available. Okay, so we just look at it in a bit. So, and then the reclaim one suggests that it didn't even dissolve. It's just like right there. Okay. So we look at the potential plant available P using extraction. That's the resin extraction and resin extraction. So it's acting like a phosphorus sink. So that's a kind of the accepted method to get an idea about what's because it's similar to kind of a plant root. So what is the potential plant availability of phosphorus in these systems, in these different sections? So you could see the control soil in there, and then also how in each section, first section, second section, third, fourth. So how monoammonium phosphate. So you saw that it's diffusing, and then you could see that at second week was the extractability. And then reclaimed struvite and manufactured struvite, we could see about 50% of the phosphorus would be extractable using resin from section. And then since we didn't see that much of a movement to further section, so we don't see enhancement in resin extractability. And then the 5 weeks, yeah, again, we kind of see in the manufacturers provide the second section slight increment, but the greater difference is this in this, even in the center section, we can see the difference in extractability in the reclaimed struvite and the manufactured struvite. Reclaimed struvite still about 55 to 60%, whereas manufactured struvite center section, the extractability increase over time. So extracted granules we did, so we can, I said like after incubating certain time, we can extract granules and then look at what's remaining. Why it is not dissolving, what is remaining. So what we did see was mostly with the manufactured struvite and the reclaimed struvite. Reclaimed struvite stayed in their in granule mostly as struvite, didn't change. You saw that map too, suggesting that same thing. And then manufactured struvite, you could see that it actually no longer as struvite. It is mostly in that, even in that granule area, it is mostly now transformed into hydroxyapatite. So what's happening is these granules are hygroscopic. So in calcareous soils, when we put these granules, they are attracting moisture. So moisture is coming towards granules with dissolved calcium. So precipitation can happen right around the granule. So depending on the mobility, if it is not diffusing at all, then you could see that it is precipitating right around the granule area or inside the granule. So this is summarizing. So although I showed only 2 weeks and 5 weeks, so the 2 days incubated granules are also tested. So just comparing the difference between the reclaim and the manufactured struvite in this soil. So the acid soil results, monoammonium phosphate, as you would expect, you could see a greater diffusion in acid soil compared to mildly calcareous soil. So you can see the PCP added in each of the sections after 2 weeks and after 5 weeks over there. And then when we are looking at the reclaim and the manufactured struvite, we did see the differences between the diffusion of it. So the manufactured struvite diffuse more, whereas this is okay. Okay, so the manufactured struvite, you could see that the diffusion was greater, about only about 77% remaining, whereas like the even in acid soil, so you could see after 5 weeks, the about 85 to 86% of phosphorus remaining. So it's dissolved better, but still it's slowly dissolving. So the experiments we conducted up to 12 weeks in not using manufactured, but the reclaimed struvite, we did see actually diffusion, the diffusion wise, it is going to be more or less similar to the soluble fertilizers after 12 weeks. So it's starting to be behaving like soluble fertilizers after 9 weeks onward. So the person resin P, and then also you could see the how the pH changes as well. So the pH, soil pH created by these granules around also contributing to the solubility. Why we see this reduced solubility? So you can see that the after 2 weeks, although the initial pH of this soil was about less than, I think it's about 5.5. So you could see that the center section of both reclaimed and manufactured struvite much higher pH. So there's residual alkalinity alkalinity effect that goes by that, so that you could see that that is also impacting the O, resulting in slow release behavior. Okay, contributing to that slow release behavior. So what we did see again with when we are looking at the reclaimed versus manufactured, so we did see both of those remaining granules had higher amount of struvite and then other type of phosphorus species as well. What we did see with the reclaimed versus manufactured, in manufactured struvite, other type of phosphorus most likely diffusing out, but this because of its struvite get concentrated. So when you are comparing struvite concentration in the original granule versus after 5 weeks, you will see more in the residue of the granule that we extracted from acid soil. So, and then so as I was presenting, I talk about some of this. So the key is whether we are using a neutral soil or whether we are using alkaline soil or acid soil. It seems that at least up to about 9 weeks or something, up to about that much, both of these struvite products have shown less solubility compared to mobility compared to conventional fertilizers. And then regardless, manufactured or reclaimed in calcareous soils, their solubilities are low. And Charlie actually did experiments with adding organic acid. What we did see in calcareous soil, addition of organic acid is not really healthy or increasing solubility. That is, then we extracted the organic acids and analyze it, and then we realize that organic acid disappeared in calcareous soil. So most likely because it is complexed with calcium carbonate, so that it is no longer is available to aid with the dissolution process, granule dissolution process. So then the acid soil, the manufactured struvite dissolve better than the reclaimed struvite. Both struvite products actually probably a suitable fertilizer in neutral and acid soils. Not through calcareous soils. Calcareous soils, even conventional fertilizers could be, challenging to use because of calcium phosphate precipitation. So that problem is there in calcareous soil, regardless. So we are doing, still analyzing data. I think Amila could analyze more Zane's data even now. He has a lot to do there. And just to show you, so we get those sections and then we can do the speciation to see what's the phosphorus speciation. So this is for bulk seams for the center section and the second. This is only showing the section 1, center section. And you could see the differences between here comparing ammonium polyphosphate, diammonium phosphate, monoammonium phosphate, and the reclaimed struvite. And then the reclaimed struvite after 5 weeks, still in that, the state as mostly as struvite. So kind of explaining why we did see the what we saw over there. So I'm not going to talk about it, just to give you an idea. So I'm collaborating with the environmental engineer at K-State, Dr. Pratap Parameswaran, and he's doing a lot of nutrient recovery, the wastewater treatment type of work. And then in that, we looked at different products, phosphorus reaction products, phosphorus recovery product. And those are either iron P or the calcium P. With iron P, when you add to soil, it's act like a sink, not as a sluice. So calcium P, actually there's a potential for improving calcium P recovery, not as a hydroxyapatite, but as a octocalcium phosphate or a little bit more soluble phosphate. So how this process works is they are doing the recovery. So we do these studies, and then those things will be feed back to their process of recovery so that they can try to improve the recovery process. So the target is to look at can we produce not exactly as soluble as the conventional fertilizers, but something not insoluble as apatite, little bit something a little better solubility. So, and this is part of my group, not that it's hard to get everyone to work picture sometimes. So the Amila is standing over there, and next to Amila, that's the Nishadi is over there, and others are working on other projects. But you know that every faculty knows that our research programs will not exist if we don't have that wisdom.